Now, we will look at power and energy in an inductor. We have already done this for the capacitor, and as you know from voltage current relations, capacitor and inductor behave similarly in a mathematical sense with the roles of voltage and current interchanged. Okay. And we will see a similar thing as far as energy is concerned as well. We have an inductor L with a voltage V across it and a current I through it, and the power, just like it is for any two terminal element, is the product of voltage and current, but in an inductor we have the voltage to be the inductance L times d I by dt, the time derivative of the current I. Substituting that here, we get L I of t times the time derivative of the current. So, as before, this looks a little complicated, but the important thing is to realize that this can also be either positive or negative. Okay. So, if you look at this product, we have these possibilities. Let us say the current is greater than 0 and increasing, which means its derivative is also greater than 0, then the inductor absorbs power, okay, or power is being delivered into the inductor. Similarly, if I is more than 0 and decreasing, that is the time derivative is less than 0, then it delivers power, and when I is less than 0 and increasing, that is it is becoming less negative, the time derivative will be more than 0 and it delivers power, because the product of a negative current and a positive derivative will yield a positive number here. And finally, for negative I and decreasing, it absorbs power. Okay. Now, for the case of the capacitor, I sketched some waveforms and showed you how this can happen. So, you can do a similar thing, but for the current waveform instead of the voltage waveform, as in the case of the capacitor. Okay. So, by now it should be pretty clear that the inductor also can either absorb power or deliver power. Okay. Now, how do we decide whether it is active or passive? Again, as with the capacitor, we look at the energy, okay, starting from 0 state for the inductor, whether it can absorb or deliver energy. If you look at energy absorbed by the inductor, and when we say energy, we have to specify a time interval. We have to integrate the power over that time interval. Okay. The limits of integration should be such that it spans the time interval. Now, let me imagine that the inductor is driven by a current source. Earlier, for the capacitor's case, I just showed the capacitor and some voltage waveform. You can think of that as a capacitor being driven by a voltage source. Here, I am driving it with a current source I, okay, and it has some variation over time I versus t. Let us say that it starts from 0 and then at time t 1 it goes to a certain value I L. Okay. So, the integral, this which gives you the energy, is integral V of t I of t dt, which is equal to integral L I di by dt over time. Okay. And the interval of integration is from 0 to t 1. As before, this looks a little complicated, but you easily see that this is related to the time derivative of the current squared, because d by dt of I square is 2 I di by dt. So, this integral turns out to be L by 2 integral 0 to t 1 the time derivative of I square over time. So, basically we have the integral of time derivative of the squared current over time. Okay. So, the energy absorbed by the inductor over an interval 0 to t 1 equals this, which is the integral with respect to time of the time derivative of I square. So, obviously, it is the function itself, which is I square from 0 to t 1. Of course, as time goes from 0 to t 1, the inductor current goes from 0 to certain value I L. So, this number is nothing but half L I L squared. Okay. So, what does this result tell us? First of all, if you change the current in an inductor from 0 to I L over a time t 1, then the total energy delivered to the inductor will be half L I L squared. Okay. Now, it does not depend on how the current gets from 0 to I L. Okay. It can do it in any which way, you will get the same answer. So, from that we can also infer that if an inductor is carrying a current I L, it will have a stored energy of half L I L squared. Okay. So, the energy stored in an inductor carrying a current I L is half L I L square. Okay. Now, as with the capacitor, when you take the inductor current from 0 to certain value I L, it absorbs a certain amount of energy, and after that it can return it all back. So, let us say the current goes back to 0, then all of this energy will come back out of the inductor into the rest of the circuit. But starting from 0, the inductor can only absorb energy, okay, because if you see the expression of energy, we have I L squared, which is always a positive number. So, it always absorbs energy and it is also a passive element, just like the capacitor or the resistor. Okay. Unlike the resistor, it does not dissipate energy, it only stores energy which can be recovered later. So, the inductor is a passive element. So, in many respects it is similar to a capacitor. In case of the capacitor, I went into more detail. The inductor I treated a little more quickly, because mathematically they are very similar. Okay. So, now I will quickly take a numerical example for the energy in an inductor. So, let us say we have a 1 millihenry inductor and it is driven by a current source like this, and the current has a certain waveform. And just for fun, let me say that the current is 0 before t equal to 0 and it goes negative okay, and it stays at this value after a certain time. Okay. So, let me say that the current changes from 0 to minus 10 milliampere over an interval of 100 microseconds, and it stays at minus 10 milliampere after t equals 100 microseconds. Okay. So, we can do all sorts of calculations with this. First, let us calculate the voltage across the inductor in this polarity. We know that V is L times the time derivative of I. Okay. So, clearly before t equal to 0, when the current is not changing, the voltage is 0. After t equals 100 microseconds, when the current is again a constant, the voltage will be 0. And between these two, from 0 to 100 microseconds, we have a constant slope which corresponds to a constant current in the inductor. Okay. And how much is that current? It will be, remember, I have taken these to be straight line segments. So, it is easy to calculate the slope. It will be 1 millihenry times a change of minus 10 milliamp over an interval of 100 microseconds. Okay. This will turn out to be minus 0.1 volts. Okay. So, this is minus 0.1 volts. Now, we can also sketch the instantaneous power versus time. Okay. So, what happens now? Clearly, before t equal to 0 or after t equals 100 microseconds, the voltage will be 0. So, the product of voltage times current will also be 0. And between these two, between 0 and 100 microseconds, it is the product of this constant and this straight line. So, it will be a straight line which has positive values, because both the current and voltage are negative, and this value is the product of these two, which happens to be
1 milliwatt.
Okay. Now, as usual, if you want to calculate the energy, you can integrate the power over time over whatever interval you want. But of course, we know that there is an easier way to do it. So, let us say we consider the energy in the inductor at t equals 100 microseconds. All we have to do is calculate half L I L square, where I L is the current at t equals 100 microseconds, and this comes out to be half times 1 millihenry times I L, which is 10 to the minus 2 ampere squared. Okay. So, this number is 10 to the minus 7 by 2 joules, or this is basically 50 nanojoules of energy. Okay. So, that is the energy stored in the inductor. Now, you should be able to carry out the same calculations of certainly the voltage from the current as well as the power and energy for arbitrary variations of current in the inductor. Okay.